Welcome to this data management section for the automatic speech recognition problem. More specifically, the automatic speech transcription problem. The data set can be gotten on this site right here. Here we have the official page for the LG Speech Dataset. It's a public domain speech dataset consisting of 13,100 short audio clips of a single speaker reading passages from 7 non-fictional books. A transcription is provided for each clip, and clips vary in length from 1 to 10 seconds and have a total length of approximately 24 hours. The texts were published between 1884 and 1964 and are in the public domain. The audio was recorded in 2016, 2017 by the LibriVox project and is also in the public domain, which you could download simply via this link right here. So here we have sample data.
The examination and testimony of the experts enabled the Commission to conclude that 5 shots may have been fired.
So there we go. That's what the audio files look like. It's the same person as it was said right here. And then the clips vary from 1 to 10 seconds. We have the file format, some statistics about the files, and then we have these abbreviations right here which could be expanded when working on or when treating our data set, because when we get to the point where we have a Mr., we're trying to train the audio model to be able to output Mr., but nonetheless this form isn't the best suited for training our model, since all the other words will be in the full form. Like if we take this example right here, we have many animals of even complex structure and all of that. We see that all those words are in their full form and not in some abbreviated form. So it's important that these abbreviations be expanded into the full form so that they match up with the rest of the data set. And then we have some of the transcriptions we don't contain or which contain known ASCII characters. As you can see here, there are no restrictions to its use. The dataset consists of excerpts from the following works, and then we could see here the authors of the dataset, that is Kate Ito and Linda Johnson. Thank them for producing or providing this dataset and making it available for the rest of the world. Once we download the dataset, here's what we obtain. We have this waves folder which contains the sounds, as you could see right here. We have 13,100 different items which we could simply use in training our model. Now, looking at this metadata.csv file, we obtain this, which is made of the file name. Like we could have this LG1, LG001, 0001 right here. We have the file name, and then we have the corresponding text like printing in the only sense with which we are present concerned differs from most, if not from all, the arts and crafts presented in the exhibition. Then we have this, which is repeated again. So basically that's how we link up the files with the corresponding transcription right here. Now we have our data. Let's see how to prepare this data so that we could make use of it in training our model. So supposing we have this kind of representation of this data wherein we have the orange dots representing data points which are actually cat sounds. So suppose when a cat produces some sound, we get some information from that and we plot like this. And then for the white dots, suppose there are some dog sounds. Now if we have to come up with some classifier which is able to separate these two regions and correctly tell us when given new input data that a particular data point belongs to the cat sound or the dog sound, then most likely this circle will do the job. Now if we change this into a polar coordinate system where each point is represented by its magnitude and its angle with respect to this origin right here, then we could have this. To convert this into a Cartesian system, we could use the relations x equals r cos theta, where theta is the angle between the horizontal axis, which is this one, and then the line which joins this point, for example, with the origin. So in that case, we have theta, and then r is basically the magnitude of the distance between the origin and a given point, say this one. So that's how we obtain r. Now, if we could convert these points to a new system, we could have something like this. Now, converting this into this new system and also being able to convert this back into this other system is very useful in this case, because right now the way these data points are being put up in this plot, it shows clearly that it suffices to use a simple linear classifier to correctly say whether a data point is a dog sound or a cat sound, whereas with this we had to use this non-linear classifier, which is more complicated than this simple linear classifier. This shows us that data representation is very important, as the way we represent our data can permit us work or build simpler models, and with simpler models we could even get better results as compared to working with very complicated models. So as usual, everything starts with the data and the way we manipulate the data. In this section, we are actually dealing with audio data. Now, suppose we have this transcription, and that the audio sound which produced this transcription was actually this. This is actually the transcription we get from this. So it's not actually a guess. It's this real transcription right here. Now, once we have this transcription, we may think of passing in this data points, because what we have here is basically data points, into our model and then train them and try to get some results from that. But it happens that in many applications which involve audio signals, instead of using this raw input signals, we tend to use the spectrogram. We should also note that some techniques may use the audio or the raw audio signal like this, or even use a mixture of the two, that's the raw audio and the spectrogram. But it's very common to find people working with the spectrogram. Now, to obtain the spectrogram from the raw input signal, which is basically this, we pass through several steps. We go through the Fourier transform, then the discrete Fourier transform, then the fast Fourier transform, before obtaining our spectrogram.